Lesson 17 is all about projectiles launched horizontally. So this is a continuation of projectile motion that we started in chapter 1. And this time, instead of the projectiles we've done so far have just been launched up, they go straight up and then straight down. Now we're going to throw something horizontally. So when you throw something horizontally, it now has a horizontal component as well as a vertical component. And then we're going to do projectiles that you launch at an angle, and that's when everything comes into play. So you can read over these notes here. But let's turn our attention to this diagram, this picture here. The question is, ignoring air resistance, which of the following correctly shows what an object would do if it's rolled off a cliff. Most people are going to look at that and say it's going to be number 2 or maybe number 1. Well, in fact, the answer is number 3, because if you ignore air resistance, if you launch something horizontally, then it will always have a horizontal component. So in other words, it's always going to be moving in a horizontal direction. It's going to be following a parabolic path. Yes. Right, and you do parabolas and quadratic functions. Quadratic functions and parabolas are the same thing. You're going to be doing that in 20-1, so they're very important in all applications of math and physics and science in general. But the important thing is that, yes, if there's no air resistance, they'll always go in a parabolic path. Now, in the real world, for example, if you throw a ball off the Calgary Tower, it's going to be more like this. It's going to go a little horizontally, and then it's going to end up going straight down because of the air resistance. So the ball will be moving vertically by the time it hits the ground in the real world. But we do these on the assumption that there's no air resistance, and therefore they always move in a parabolic path. Therefore, they always, until they hit the ground, have a horizontal velocity and a vertical velocity. All right, let's get to some problems here. So the trick to these questions and for lesson 18 is to separate everything into components. And once again, those components are mutually independent. The horizontal motion of the projectile is completely independent from the vertical motion of the projectile. And we're going to see that the horizontal motion of the projectile is governed by one formula and one formula only, and that is this, v equals d over t. Why is that? It's because the horizontal motion of the projectile is a constant uniform velocity, constant velocity or uniform motion. So it's always going the same velocity horizontally. In terms of the vertical component, it's governed by all the kinematics equations that we learned in chapter 1, which I'll leave you to review. So again, you can read over this, talks about horizontal and vertical components. And here's a good diagram that you should know. You can see the blue vectors represent the horizontal velocity, and the blue vectors are the same size throughout. The red vectors represent the vertical velocity, and as you can see, because it's accelerating vertically as it goes down, they're increasing all the time. And that is why the horizontal, the horizontal component uses that formula and that formula only. You cannot use any other formula for the horizontal component in projectile motion. The vertical components, you can never use that formula because vertically it's accelerating all the time. You have to use these formulas. Oops. There we go. There's your 5 kinematics formulas, and you have to use those exclusively for the vertical component. Okay, here we go. Then it talks about parabola, again, very important, and talks about thinking horizontally. When you're asked a question with horizontal projectiles, ask yourself, is it a horizontal component or is it a vertical component? Here we go. Example number 1. I throw a ball off the edge of a 15-meter tall cliff. I threw horizontally at 8 meters per second. There's your diagram. 8 meters per second horizontally. So initially it has only a horizontal component. And then you've got a bunch of questions related to it. So first, let's draw just a basic diagram. It's going to go. So there's the path of the projectile. And the first thing we're going to do is identify what we have in regards to each component. So we're going to write horizontal. And we're going to ask ourselves what information is given in the question that applies to the horizontal component. There's only one answer here, and that's the 8 meters per second, because it said I threw it horizontally at 8 meters per second. So that is the velocity. And it's not the initial velocity, because we've already said horizontally it's constant velocity, so it's always going at 8.0 meters per second. Do we have the distance, which is this? And the other term that we use for that, the distance horizontally, is the range. And we don't have that. Do we have the time? No, we don't have the time either. So that's what we've got going horizontally. What do we have going vertically? Okay, well, vertically, obviously, we have gravity, because it's going to accelerate according to gravity as it goes down. What else do we have vertically? Well, we have the displacement. Here's the vertical displacement. It's a 15-meter tall cliff. So the vertical displacement is actually negative 15 because it's going down. Do we have anything else? And the answer is yes. We actually have the initial velocity, which is 0, because it has no vertical velocity initially. Do we have the time? No. Do we have the final velocity? No. No, no, no on that one. And you can't say it's 0 when it hits the ground. Obviously, it's 0, but we're always talking right before it hits the ground. So that's what we have horizontally. That's what we have vertically. And now we can look at the first question. Determine how much time it takes to fall. Well, you can see, because we've listed all our variables, that time is common to both the horizontal and vertical components for very obvious reasons. If I throw a ball, it's clearly in the air horizontally for exactly the same time as it's in the air vertically. So which components are we going to use? Well, let's look at the horizontal components. Can we use that? No, because we've got 3 variables and we only have information for one of them. So that's out. We need 2 variables to be able to solve for the third. What about vertically? Can we solve for the time? And the answer is yes, we can, because we have 3 known variables and 1 unknown variable. So we're going to use an equation that has these 4 variables in it right here. There we go. And that equation is, let's go to A. You don't need to write that. I'm just going to write it so that I'm reinforcing that I'm going to use the vertical component. And the formula that we have with those 4 variables is this one. And again, like most examples that use this formula, the VI is going to be 0. So really, so this is 0 right here. This whole thing cancels out, leaving me with this. And I'm going to solve for t. T equals, hopefully you've done this enough time so that you've got it memorized. The t equals the square root of 2d over a. Plug in the numbers that you have. And get the answer. And you'll note that the negatives cancel each other out, which is great because you can't take the square root of a negative number, and you get an answer of 1.75 seconds. Okay, now this is great, 1.75 seconds, because now we have 1.75 seconds right here. So if at some point they ask us what is the horizontal displacement, now we have enough information to do that. Okay, B says determine how far from the base of the cliff it hits the ground. Well, there it is, right there. From the base of the cliff, determine how far. So they want this distance here, which we call the range or the horizontal displacement. And we can do that quite easily because we have the velocity and we have the time. So let's go even further from B. So B will be V equals D over T. D equals VT, so it's just the velocity, 8. Nice easy one, 14 meters. So it lands 14 meters from the base of the cliff. C says determine how fast it is moving vertically when it hits the ground. So it's pretty obvious we're going to have to use the vertical component. And what are we solving for here? We're solving for this one, VF. VF. And we're going to try and use only information that's given to us in the initial question. So of course we can do that because we have 3 pieces of information here and we're looking for the 4th. So what formula has VF, VI, A, and D? And that is our good friend. Let's see. And again, we're talking about a pretty straightforward answer here. So that's going to be once again, the negatives cancel out, which is a good thing because we're going to end up taking the square root of this number. And once we do that, we get 17.2. Circle our answers. Good, so there we go. We've got 3 out of 4. And the last question says, determine what is the total velocity when it hits the ground. Now that's the trickiest one because they want the total velocity. They want the horizontal and the vertical components. Extend the page. So D, both H and V components. Right, which means when it hits the ground, remember it always has a horizontal component and it always has a vertical component because we assume that there's no air resistance. So once you realize that, it's not too difficult because you know that its horizontal component is 8.0. We just calculated its vertical component, 17.2, and what is the total velocity? Right there. The resultant vector. Here are vectors again. Vectors are going to haunt you for the rest of your physics days. In a good way, good haunting. There it is. Solve for R, solve for theta, just like we've done in multiple vector problems. R turns out to be 19. Meters per second. Theta turns out to be 65 degrees. And so your answer for this question, you got to be careful you word this question correctly because we're not dealing with north, south, east, west. We're dealing with down and we're dealing with horizontals and verticals. So the best way to express this answer is 19 meters per second, comma, 65 degrees below the horizontal. Right, and let's just go over that. 65 degrees below the horizontal. Here's the horizontal, and we're going to go 65 degrees below it. So that's the best, if somewhat, if not the clearest answer, but that's the best way to express the answer for this question. And that, I think, ends lesson 17. It was a long one, but it's a goodie. We'll see you for lesson 18, which is even goodier.